Hello students, let us discuss torque on current carrying loop in a magnetic field. Let us consider a loop PQRS having length L and breadth B, which is kept in a uniform magnetic field B, and the plane of this loop is making angle theta with the magnetic field. Okay, this angle theta. A steady current I is flowing in this loop. We know that a current carrying loop behaves like a dipole, magnetic dipole. Okay, if current is flowing anti-clockwise and if we see it from one side, so south pole will be there and from the other side north pole will be there. So the two poles kept very near to each other will form a magnetic dipole. So it will experience a torque. It is just like as electric dipole, when it is kept in an electric field, experiences a torque. So just like that, this current carrying loop is also experience a torque. So let us discuss about that torque. In previous lecture we have seen that a current carrying conductor kept in a magnetic field experiences force, which is given by F is equal to I L cross B. So the force experienced by this arm PQ will be F will be is equal to F1. F1 will be is equal to I PQ cross B, where PQ is the length of this arm, or you can say current element. So it is given by I L B sine 90. You see the angle between magnetic field and this current element is 90. Okay, so F1 is given by I L B sine 90 is equal to I L B, because sine 90 is equal to 1. And if you apply Fleming's left hand rule, you will get its direction, and the direction of force will be out of the paper, or you can say outward. Okay, next come to arm QR. Force F2 experienced by this arm will be given by F2 is equal to I QR cross B, where QR is the length of this part QR. Okay, it is B. So F2 is equal to IBB sine theta. Here the angle between this current element and magnetic field is theta. Just like this. Okay. So it is IBB sine theta. And the direction of force will be downward. Similarly, if we find force experienced by arm RS and SP, so we will get F3 is equal to ILB, just like F1. Okay, and the direction will be inward into the paper. Okay, and the force F4 will be ILB sine theta, and the direction of force will be upward. Now you see four forces F1, 2, 3, 4. Out of these four, F2 and F4 are equal and opposite to each other. Okay, F1 and F3 are equal in magnitude, but they are not opposite, you can say, acting parallel to each other. So net force acting on this loop is 0. Okay, you see F2 and F4 are equal. F2 is equal to IBB sine theta, and F4 is also IBB sine theta. This is in downward direction, this is in upward direction. Okay, so these two forces are equal in magnitude, opposite in direction, and acting along the same line of action. So these two cancel out each other. What about F1 and F3? F1 and F3 are also same in magnitude. This is ILB outward, ILB inward. So both are equal in magnitude, but they are parallel to each other or opposite but having different lines of action. Okay, so such type of forces cause torque. Torque is the turning effect. Okay, it gives a turning effect to the loop, and this loop moves in this magnetic field. Okay, and we know that torque denoted by tau is given by either of the force and arm of the couple. If two equal and opposite forces act on a length, okay, so tau is given by this, or you can say either of the force means F into perpendicular distance between two forces. So the torque tau is equal to either of the force and perpendicular distance between them. So this is another diagram of two forces F1 and F3, which are acting along different lines of action. Okay, F1 is equal to ILB, F3 is also ILB, but their lines of action are different. They are parallel to each other. Okay, and the perpendicular distance between these two forces, the total length of the arm was B, and perpendicular distance between these two points will be B cos theta, you see. So the torque tau is given by either of the force ILB B cos theta. And what is L into B? Length into breadth will give you area of that loop. Okay, so we can write it like IBA cos theta. Okay, if n turns are there of that current carrying loop, so we can write it like tau is equal to NIBA cos theta. Okay, we have seen that the plane of the loop is making angle theta with that magnetic field. If we talk about area vector of this loop, what is area vector? It is the perpendicular, it is the normal drawn on the area, on the surface. So area vector is making angle alpha with magnetic field B. Then you see theta plus alpha is equal to 90 degree, or theta is equal to 90 minus alpha. Putting this value in equation number 1, we will get tau is equal to NIBA cos 90 minus alpha. 90 cos 90 minus alpha is equal to sin alpha. So we get expression for torque tau is equal to NIBA sin alpha. Okay. Now I have told you that this current carrying loop acts like a magnetic dipole, which is given by M. M is equal to IA, the current flowing through that loop, and area of that loop, area in the form of vector, area vector. Okay, so M is equal to IA, or if n turns are there, so M is equal to NIA. So putting the value of M here in this equation, what will get? NIA will give us this magnetic dipole M, this is magnetic field B, and sin alpha, or we can write it like tau is equal to M cross B in vector form. Okay, cross product of two vectors is a vector quantity, so torque tau is equal to M cross B, or you can write like NIA cross B, where A is the area vector which is perpendicular to the plane of that loop. Okay, so this much torque is experienced by the current carrying loop. Now let us see the cases of the torque experienced. Okay, case 1, when theta is equal to 0. When theta is equal to 0 means the plane of loop is parallel to the magnetic field. You see, when theta will be 0, the plane of loop, plane of coil is parallel to P, or you can say at that time alpha will be 90, isn't it? Perpendicular to that plane will be 90 degree at that time. So if theta is equal to 0, then tau is equal to NIBA cos 0, means NIBA, that is maximum. Maximum torque will be experienced by the coil, by the loop, when theta is equal to 0, means when plane of loop is parallel to the magnetic field, and this condition is called a radial field. We will talk about this radial field in case of galvanometer. Okay, in second case, when theta is equal to 90 degree, means when plane of loop is perpendicular to the B, when it is 90, exactly like this. Okay, then tau will be 0 because cos 90 is 0. Then no force will be experienced, by no torque will be there, or you can say minimum. The value of torque will be minimum, and in this case the value of torque will be maximum. So this is about torque experienced by current carrying loop or that coil in a magnetic field. Let us discuss one question, one numerical. You are given a square shaped coil having area 100 centimeters square, number of turns 200, the current flowing through that loop is 5 ampere, which is kept in a magnetic field 0.2 Tesla. Okay, find torque when plane of coil makes angle 60 degree with magnetic field B. And the other part, second part of the question is, in which orientation coil will be in stable equilibrium. Okay, so let us see what is given to us. Area is equal to 100 centimeters square, that is 100 into 10 power minus 4 meters square, which is equal to 10 power minus 2 meters square. Theta is given 60 degree. Angle between plane of the coil and magnetic field is 60 degree. Okay, so if theta is equal to 60, then alpha is equal to 30 degree. Okay, so tau is equal to NIAB sine 30, putting all the values, n turns, and are the number of turns 200 into current 5 ampere into area 10 to minus 2 meter, and the magnetic field is 0.2 Tesla into sine 30. Sine 30 is 1 by 2. So on solving it, calculating it, we will get the value 1 Newton meter. And when it will be in stable equilibrium, for stable equilibrium, alpha should be 0. Alpha should be 0, or you can say theta should be 90. Means when area vector, the angle between area vector and the magnetic field is 0, then it will be in stable equilibrium. Or when the angle between plane of the coil and magnetic field is 90, then we can get stable equilibrium. Okay, so this is all about torque experienced by loop in a magnetic field.